Hey folks, we are continuing on in Unit E, Sampling Distributions and Estimation, and we're going to introduce a new concept here, the finite population correction factor. So let's take a look at what this paragraph says here. For most problems, the size of the population is unknown or extremely large. So for instance, we are talking about, say, sampling Canadians, and there's millions and millions of Canadians, and we're going to take a sample of, say, 1,000 or something. That sample actually is very, very small compared to the whole population. Same with Albertans, right? There's 3.5, 4 million Albertans, whatever, and if we take a sample of a few hundred, then that's very, very small, and we're hardly denting it. But what happens if you have a fairly small population and your sample is large relative to the size of the population? When we have that, we tack on this thing called a finite population correction factor, or an FPC, and it's this part right here. And what it does actually is, when we get into confidence intervals, what you'll see is that it actually makes the confidence interval smaller, representing that there's less uncertainty about our estimate. And it'll make more sense when we get into confidence intervals. So you just want to kind of hold that one for now. But it's actually a good thing, is that we're saying that we know we have sampled a significant proportion of the population. And so we know a lot about the whole population, so it makes it easier to infer the characteristics of the population. The rule that we tend to use here is that if you know what big N is, and of course little n, the sample size, then as long as little n is 5% or more of big N, then you should be tacking on an FPC factor. You know what I do is, if I know what big N is, I just use it anyways, unless it's really, really big. Okay, I'm not going to take a sample of 100 people out of, say, 20 million adults in Canada. 100 out of 20 million adults is hardly making a dent at all, so I don't use the FPC factor there. But in the examples that we have below here, you'll see that the FPC factor should be used because the sample size is a significant proportion. Our formula is, it looks a little uglier, but just to recognize that all we've done is we've changed the denominator. So instead of it being sigma over the root of n, it's sigma over the root of n times the FPC factor. That FPC factor will always be something less than 1. So it actually makes this whole term here, which in stats we call the standard error of the mean, is actually smaller. Because we have sampled a large portion of the population, right? So standard error of the mean is sigma over the root of n, and we would tack on an FPC factor if we need to. Let's take a look at an example, and then I'll leave the other one for homework. So page E9, suppose it is known that the 200 instructors at RDC, by the way, it's actually much larger than that, but in terms of maybe full-time and so on, it might be close to that. So there's 200, it would be big N here. Watches television an average of 15 hours per week with a standard deviation of 5 hours. What is the probability that a random sample of 30 instructors will yield an average of at least 16 or more? I want you to take a look at the symbols that I've used here. The first sentence is talking about the population. It doesn't use the word sample. So they're all population parameters. So suppose it's known that big N, 200 instructors at RDC, watched television average of mu, 15 hours per week, with a sigma of 5 hours. Then the next sentence is where we introduce the sample. So this is a really important word, because that tells us now that we're using sample statistics. So we've got a sample then of little n is equal to 30 and an x bar equal to 16. Hey, I'm just going to do an aside here and just notice here that what we've done in our course here is to say that we've talked about the size, we've talked about the mean, and we've talked about the standard deviation. And we've looked at populations and we've taken a look at samples. And the size of the population is big N, but the sample is little n. The mean for the population is mu. The mean for the sample is x bar. And the standard deviation of the population is sigma. And the standard deviation, which we actually don't need here, is S. So that goes back to Unit C. We've seen that all before, but it's good to just review that. All right, let's go through the steps here. Step number 1. What do we know about the population? Well, X is normally distributed. Or is it? Now, it actually doesn't say anything here about the distribution of television times being normally distributed. But is that a problem? And the answer is no, because of the central limit theorem. Remember, the central limit theorem says that as long as your sample is at least 30, then the central limit theorem kicks in, so it doesn't matter how the population is distributed. So what we've got here then is that we don't know that it's normally distributed, but because n is at least 30, we can continue. The mean is equal to 15, and the standard deviation is 5. So that's what we know about the population. But the CLT kicks in. Okay, and the CLT will say that the x bar will be normally distributed with a mean of 15 and a standard deviation of 5 divided by the square root of 30 times your FPC factor, which is 200 minus 30 over 200 minus 1. All right, let's take a look at how this works here. Now, incidentally, on an exam, you wouldn't have to write that down. You could just simply write down the probability here that we are looking for the probability that we have an x bar of at least 16. So that's this statement. Let me change colors here. A sample will yield an average of at least 16 hours per week. So that's what we're looking for. Let's draw that as a picture. Ooh, that's not very good. All right, so let's redo that. Well, it's supposed to be a normal distribution. It's a distribution of the x bars, and according to the central limit theorem, the mean is going to be equal to 15, and then the standard deviation will be this thing right up here. And we're taking a look at 16. What's the probability of getting at least 16 hours? So in other words, what is that area there? All right, let's standardize. Step number 3. Z is equal to x bar minus mu over sigma divided by the square root of n times the FPC factor. By the way, it doesn't get any worse than this. This is about as complex as the formulas get. That's going to be 16 minus 15 over 5 divided by the square root of 30. And then big N is 200 minus 30. So you'll notice that the 30 is at least 5% of 200, right? 30 divided by 200 there is, it's, well, 15% over 200 minus 1. And you get out your calculator, and when the smoke clears on that one, you're going to get 1.19. So now we go to a normal distribution. This would be step number 4. And we're looking for the probability of getting a z greater than 1.19. And so we've got a z, and we've got 1.19. So these pictures should look the same, right? You're looking for an upper area here, 1.19. And what we would do is we would go back to our z table. Let's just go back there. And, oh dear, didn't take that last number. Here we go. Okay, here's a normal distribution, and we're looking at 1.19, and so that gives us this value right here, right? Now, remember that that is this area right here. So this area is going to be 0.5 minus that value. So instead of 38%, it'll be about 12%. So let's go back to where we were. And see where we're at. Right there. Okay. So what we had here is, I'm just going to change colors here and say that this area here was 0.3830. And then we're going to subtract that from 0.5, right? Because the whole upper half of the distribution is 50%. And so that leaves us with this red area here is 0.1170. There's your answer. So it's about 12% is your answer. Okay. That's where I'm going to leave you. I'd like you to do the next one for homework. So pick out all of your symbols, all of your numbers, give them a symbol. By the way, when you're dealing with these big numbers like this, instead of, because they're all in millions here, you can just actually make this 8 and 2 and then 8.25. That will just make it easier because the units, they'll cross out there in the formula. So that's where we're going to end it today. Thanks for listening.